to put this in the language of math, we need linear algebra now. Okay. So, here is where your knowledge of linear algebra will come into play. So, let us start from the top. Those of you who have done linear algebra, they know that if an operator has a differentiation or an integration, then that operator is it's a linear operator, right. So, this is anyone who has taken a basic course in linear algebra knows that that the operator is a linear operator. We have seen the kind of operators that we have had so far, right. Del squared plus k squared, differentiation operators are there. Then when we went to integration, there was an integral sign inside it. So, there's differentiation, there's integration, there is nothing more fancy like exponential or something like that, right. So, the operators that you get in computational electromagnetics are linear operators, and the great relief or the great sort of saving grace about it is that linear operators we can talk about in the language of linear algebra. So, all the tools of linear algebra can be applied to these problems to solve them. Okay. So, that is what really saves us. We could not do this if our operator was not linear. Okay. So, let us take a very general problem over here. So, capital L over here, this is some operator, okay, acting on phi and giving f. So, the usual interpretation is what we will use, that f is known and this psi over here, or phi rather, is something we want. Okay. Now, in terms of an operator, right now we have not discretized anything, it is just an operator. Okay. So, what does any operator do? It is going to take one space to another space, right. So, I can say that, say phi lives over here and the operator takes it, let us say call this some space V, and the operator over here, this L, takes it to another space over here F W. At least we hope that F is in the space, right. So, what I am describing is that these are, so let me not write F and phi yet over here. So, L over here is the operator that takes one space to another space. So, the left hand side space is what would be called, what would you call the space on the left hand side? The domain, right. So, I will call this the domain, and the domain gets mapped to the range, right. So, this is the range. Okay. So, the domain, the symbol for that is dl and the range symbol is r of l. Okay. Right. Now is when we go to the discrete world. So, when we discretize this continuous space over here V and W, it gets discretized also. So, it becomes a finite dimensional vector space. Okay. So, it becomes V n, let us call it, and similarly W becomes W n. Okay. So, these are finite dimensional vector spaces. To characterize a vector space, what is the most sort of basic building block? Basis functions, right. So, basis functions, so it is characterized by a set of basis functions. So, let us call them say B n of r, right, n is equal to 1 to n. Okay. We do not even need this over here, just n vectors. These n vectors will characterize a vector space, and for these n vectors to characterize the vector space, what is the requirement on these vectors? Right. So, first is that they should be linearly independent, right. Second, need not be orthogonal, I can have non-orthogonal basis also. So, when will I call a set of vectors a basis for a vector space? They should span the whole vector space, right. So, for example, if I give you 3-dimensional space, x vector and y vector, they are linearly independent, but they do not span 3-dimensional space. So, these vectors put together should span the vector space. Okay. So, these are the two requirements to be called a basis. Okay. Fairly simple stuff now. I mean, we already sort of know this, but we are just formally putting it into the language of math. So, therefore, for the domain I need a basis, and for the range also I need a basis. Okay. So, I am going to call the set of basis vectors for the domain, I am going to give the symbol B. Okay. So, Bn, and for the range I am going to use a slightly different symbol, I am going to call them Tn. Okay. So, the way to remember it is sort of what will come later on. For the domain I am going to call these basis functions, and for the range I am going to call these testing functions. That is why the letters B and T. Okay. So, it will become clear as we go why these letters or words basis and testing. Okay. In order for us to solve this equation, if I just go back to the original equation over here and I say give me a solution to this, right. So, very beginning of linear algebra, what do you say should be a condition on f for you to be able to solve this equation? The range, right. So, if I am going to be able to solve this equation, f should be inside this range. Otherwise, there is no way that L will map anything and get me f, right. So, f must be in the range of L. That is kind of obvious, but I am just stating it anyway. Okay. So, this is sort of a brief review of linear algebra that we will use, okay, because the whole method of moments is a very nice tool from linear algebra only. It uses basis vectors and it uses inner products, nothing more complicated than that. Okay. Is this fine so far?